Digitizing records XY coordinates from trace map features, but they're still arbitrary and transformation is required. Tablet digitizing uses a puck and needs GCPs to convert coordinates into real world values. On screen digitizing traces a scan map and also requires GCP for accuracy. Coordinate transformation turns arbitrary coordinates into real world or between systems such as RSO and Cassini. Affine transformation adjusts shift, scale, rotation, and skew using 6 parameters. GCPs are known real-world points from Jupyter Maps, grids, GPS, or surveys. GPS can be computed using bearing and distance to find new coordinates. Residuals and RMSE check transformation accuracy. The lower values means better results. Transform data is merged into existing datasets for alignment. And finally, the cleaning fixes digitizing errors and ensures positional accuracy.
For the coordinate system, coordinate system is a fundamental in GIS because it allows us to accurately describe the position of features on the Earth's surface. So there are two main types of the coordinate system: geographic coordinate system, which use latitude and longitude in degrees, and then the projected coordinate system, which represent location using x and y coordinate system in meters. So basically, in Malaysia, for the topographic mapping, it commonly based on the RSO system, while cadastral mapping in Peninsular Malaysia use the Cassini-Solnit system. So the previous datum such as MRT48 and BT68 have now been replaced by the geocentric national datum, which is GDM 2000. Because the GPS operate in WGS 84, so coordinate conversion is usually required before integrating data into the local mapping system. And then we need to use the correct coordinate system so that all spatial data align properly and can be analyzed accurately.
First of all, GIS needs reliable technology, good quality data, and user interaction. The focus is on information that is accurate, current, and easy to access. For example, geoportal platforms and multi-user online GIS. Next, surveying and mapping today use digital and automated tools. These make data collection faster and more precise. Instruments like the total station and LiDAR are common example. In addition, GPS is part of the bigger GNSS family. Systems like GPS from the United States and Galileo from the European Union all work under the WGS Active Coordinate System. Furthermore, GPS satellite orbit the Earth at about 20,200 kilometers. They send signal with time and position. Different generation such as Block IIR and Block IIF have improved accuracy and usually 4 to 12 satellites are visible at once. Moving on, GPS finds position using triangulation. It measures how long signal travel from satellite to the receiver. Distance is calculated with velocity times and pseudo-random codes help keep timing accurate. At the same time, GPS accuracy can be affected by error. These include atmospheric delay, reflections, clock problems, and satellite geometry. DOP value show the quality of positioning. Example are ionospheric, delay, and multiple reflection. On top of that, differential GPS and RTK use a base station and a rover to cancel error. This gives very high accuracy. In Malaysia, networks like MyRTConnect and MASS are used for professional surveying. Finally, GPS support GIS capturing point, line, height, and control data. It is used for updating database, mapping infrastructure, and collecting ground control point. For example, GPS help in new route mapping and in improving aerial imagery. In conclusion, GPS and GNSS work closely with GIS to provide reliable spatial data. Together, they ensure accuracy and efficiency in modern mapping. Thank you for listening.